Okay, so good. So sorry, folks, for people who are on the videotape, you missed out some good stuff, but we'll continue on. All right. So we want to turn this idea from a theoretical result to a system result, and the key to that is to go from the point-to-point setting to the multi-user setting. Okay. So this is actually interesting, because if you think about the traditional ways of designing cellular system, is if you look at the GSM or the CDMA case, we talked about it yesterday. In both cases, we are trying to reduce the problem from a multi-user problem. The problem is intrinsically multi-user, but the intrinsic approach was to decompose it into individual point-to-point problems so that we can solve them. Okay? For example, in CDMA, we are essentially making the interference look like Gaussian noise. In GSM, we're orthogonalizing each link so that it becomes a point-to-point problem. So now we're going to take a different approach, and we're going to ask a more fundamental question, which is, if I start with a multi-user communication system, what is the capacity of the system? Okay. And so I start with this situation. This is a downlink, but you can apply the same ideas to the uplink. You have a base station is sending traffic to K users, independent information. Everybody is talking on their own cell phone. Independent information, so I'm serving information to these guys. I can ask the question of what is the capacity of this downlink. So this is a downlink. By capacity, I mean what is the total throughput I can get to all these users? Total throughput, system throughput. Okay? So now I'm not reducing to a point-to-point problem a priori. I'm asking a fundamental question about the whole system, And it's an architectural question. And if you plot the capacity of, so what is the capacity? This is bits per second per hertz of the whole system. If you plot it in the Rayleigh fading environment, okay, so this is, each link is Rayleigh faded, independent of each other, okay, then what you see is that as a function of the number of users, so now I'm plotting not as a function of SNR anymore. I'm fixing the SNR to be, say, 0 dB. And I'm plotting as a function of number of users the performance, the spectral efficiency. And you see that compared to the AWGN, for one user, you're worse than the AWGN. We know that already. CSIR is less than AWGN for one point-to-point communication. For more than one user, it is increasing and beating AWGN capacity. Okay? So this is another example of opportunistic strategy at work. Okay? What's happening here? Actually, if you think about what's going on, it's not that surprising. Because what's happening here is that the base station is tracking the channel of all the users. Okay? And whenever, at each time, you basically pick a user to transmit to who has the best channel at that moment. And you blast the bits to that user. Next time around, the channel may change because we're dealing with a fast fading situation. You choose another user whose channel is very good and send it to that user. Okay? And so why does this increase with the number of users? Because as there are more users in the system, the user who has the best channel is likely to be higher. By transmitting to that user, you get a more bang for the buck, and your aggregate spectral efficiency is higher. So that's why there's an effect in terms of increased number of users. This effect was called by these folks, Nopin and Blake, called multi-user diversity, in the sense that in a network where you have multiple users, hopefully the network does have multiple users. Otherwise, not so good. Then there's intrinsic diversity because of the various fading channels. And by scheduling with the strongest user, I can get a biggest bang for the buck. And its spectral efficiency increase. So this is an opportunistic strategy. But it's not so much opportunistic over time only, but also over the user dimension. Okay? Now, so let's think about this a little bit. And now let's think about how I'm improving the situation over the point-to-point situation. Okay? In a point-to-point situation, we have the problem being that the benefit is in the energy limited regime rather than the bandwidth limited regime. Okay? Here, the benefit actually extends to the bandwidth limited regime as well. And the reason is the following. Okay? In the point-to-point situation, if I have if I have a peak power constraint, then I transmit when the channel is good. But when the channel is not so good, I still should transmit anyway, because I can't save up power. Okay? So saving up power is kind of a very foreign concept for a cellular communication system. But now, in a multi-user situation, the situation is different. So even though I may not have an average power constraint, maybe I have a peak power constraint, if I focus on one user, when that user channel is not so good, I have other things to do now. What can I do? I can transmit to another user. And that's the biggest difference. Why this result is now useful. Because now I can transmit to different users, even if I only have a total amount of power which is I want to consume, which is fixed at all times. I have things to do. Whereas in a point-to-point setting, I have nothing to do other than sending it to the user. Okay? So that's an important point. And that, in some sense, is the first evidence of how this idea could become useful. Okay. So it is not enough, though. It is only suggestive that it's useful. To turn it into a system idea, we have to still take a few more steps. And the next step comes in 1999. So the history of this whole thing is interesting. So the point-to-point result was obtained by Goldsmith and Varaya, very nice result, in her PhD thesis in mid-90s. Knopp and Humblay generalized that result to the multi-user setting, the result I showed you earlier. And now comes 1999. So I went to Qualcomm. I spent half a year at Qualcomm. And they have this system called 1xEVDO. Presumably, Ramesh was saying that this system was experimented in the San Diego campus as well, but now it's deployed nationwide. And they were designing the system, and I looked at that system, and I thought, you know, this system is a good candidate for applying this idea. Okay? And the system is the following, in case people who are not familiar. I don't know if Qualcomm forced everyone in UCSD to be familiar with all the systems, but base station here, sending traffic in a downlink. Okay? How is the channel information actually acquired here? Each user measures the channel based on a pilot. So there's a very strong pilot that the base station sends out. Every user measures the channel, and then it requests a rate. What does it mean requesting a rate? Requesting a rate means the following. It means that it measures the channel, and it predicts, okay, if the base station decides to send me in the next time instance, then my channel is likely to be so-and-so. Based on that, it requests a rate saying, you know, if you decide to send to me, then you should send at this rate. That's all. Everyone does the same thing. And the base station does a TDMA strategy. At different times, it schedules different users depending on what it wants to do. Okay, so in this case, the red and green user. So obviously, this is a very natural tie-in to the information theoretic setting that I talked about earlier. Okay, so now let's see how we can apply that idea. So now we're going to apply that idea. So, you know, I was there for 5 months, and I came to San Diego. Wow, beautiful beaches here. And I thought, I got this idea day one already. I should apply it. 1 week, I'm out of here. I go to the beach for 4 months. And I tell my people at Berkeley that I'm working very hard here. And so I showed them the first week. I did some simulations. I showed them, you know, this is great stuff. It gives you like a 2-fold increase in capacity and so forth. So let's see some curves. So here is an example of a situation where I have 2 users, red and blue users. I plotted over the time slot. Each time slot in this system is 1.6 millisecond. So here we're talking about 3 or 4 seconds here. A few seconds, is that right? 1.6 millisecond, so 3 or 4 seconds, yeah. Okay, so the red and blue requested rate is changing because the channel is fluctuating, okay? This is a situation where you have 2 users in the cell. Okay, so you have the cell setup is the following. You have your tower here. I have a user 1 here, and a blue user, say here. All right. So roughly the same distance from the base station. So if you look at the channel variation, so the requested rate is varying with time, and the variation is due to multipath fading. However, the average requested rate for the blue and the red trajectory is more or less the same. Why? Because they are roughly the same distance from the base station. Okay? So now I apply the knob and blade strategy, and the strategy will naturally translate to I schedule a user when that user requested rate is high. All right? I compare the requested rate, I schedule the user with a high requested rate. So that maximizes the system throughput. That's what information theory tells me. Okay, and it does. It's also very fair. So from a system point of view, it's also very fair. Why? Because both users, the red and the blue user, are essentially now being served when the channel is very good. So both users are benefiting equally from this gain. So it's fair and maximizes system throughput. Best situation. However, unfortunately for me, this is not the real world. This is still an academic world. The real world is this situation. The real world is that you're going to have a population of users, okay, distributed in your cell. Some are closer by, and some are further away, okay? This is an example of a blue user now who is very close by. His channel, average channel, is very strong. Remember, across the whole cell, the variation is very high. It could be 20, 30, 40 dB at a global level, at a macro level. So the blue guy is actually probably 20 dB in this example, above the red guy. Okay? So if I follow the same strategy of serving the best user at any time, okay, then what I get an excellent system throughput. You know, so I can tell, Verizon can tell its customers, you know, we got like 5 megabits per second in the sector here. However, if you happen to be the red guy, you don't get 5 megabits per second. You actually get almost 0 megabits per second. All right? Why is that? Because if I serve the best guy, then the red guy, I just can't use the S word. It's just, can I use the S word just once? The red guy's screwed, right? You know? So he can't get it right. All right? And so that's no good. That's not good. So from a fairness point of view, this is not a good strategy. And it's not good to marketing either if you are the red guy. And Verizon tells you, you know what? When you move your house to closer to the tower, then you'll get a great rate. So these few months, no problem. Wait until you move your house. You know, that's probably not the best marketing strategy. And so what we want to do is therefore try to translate the multi-user diversity benefit even in this setting. That's what I want to do. And that was my task for the remaining few months. And if you look at that situation, what I really want to do, okay? What I really want is to be able to improve both the blue guy and the red guy. So what I really want is I want to transmit to the blue guy when the blue guy is near the peak, and transmit to the red guy when the red guy is near the peak. Okay? And because these channels are fluctuating more or less independently, the blue and the red are unlikely to peak at the same time. And therefore, by scheduling, the peaks are not synchronized, and so therefore you will have an opportunity to schedule different users when they're at the peak at different times. And that's how I can get the gain. Okay? So I want to serve each user when it's at the peak. And the next question is, what does it really mean by the peak? And that's where the latency timescale, which we focus on a lot, comes in. So if I wait for the peak, if my latency timescale is like 10 seconds, then obviously I can wait a long time for a very high peak. So the peak is the maximum of the process over 10 seconds, and it's very high. Okay? However, if my latency is only 1 second, then I cannot wait for 10 seconds. So the peak at the timescale of 10 seconds makes no operational sense to me. So therefore, the latency defines essentially what it means by the peak. Okay? So the peak is essentially the maximum of the process in a timescale which is defined by the latency timescale. Okay, so how to translate this idea to a scheduler? So this scheduler is called a proportional phase scheduler because it optimizes certain principles that only economists are worried about. And this is the algorithm. It's very simple. It schedules the user with the highest ratio, RK over TK. So RK is the current requested rate of user K. So each user, remember, is requesting a rate as a function of what he predicts the next time slot's channel will be. All right? And TK is the average throughput of the user K in the past TC time slots. So this is the rate that the user has been getting in the past TC time slot. So TK is a measure of essentially how good that user is on the average. RK is the measure of the instantaneous channel strength. The ratio is a measure of how close that user is to the peak. And I compare these numbers, and by serving the user with the highest ratio, I'm essentially trying to schedule the user when it's close to the peak. Okay? And when you look at a special case, when all the users are symmetrical statistics, then by symmetry, the TK will be the same across all users. The denominator will be the same for all users, and therefore only the requested rate matter. And you end up serving the user with the highest requested rate. Back to the knob and blaze strategy, which works perfectly for symmetric channels. So this is a generalization of that in some sense. Okay? And it works. So let's look at some performance. Simulated situation, but a lot of experiments have been done. This scheduler is actually the one implemented in almost all systems. Okay. If we look at 3 environments, so I'm looking at 3 environments here. In the fixed environment, okay, that's a good ringtone. All right. In a fixed environment, I'm the mobile. Here's the tower. So I may be in a house or something. I'm like on my laptop working, fixed. Now, the channel will still vary because, you know, there may be cars moving outside your apartment. There may be people walking around you. So the channel will still be varying. And I model this as a Rayschen fading environment where you have a fixed component which is not moving and a fluctuating component which is moving, the red curve. And this shows you the gain in performance as increasing with the number of users, multi-user diversity gain. The blue curve is a low mobility environment where now I start walking with my device, small device, hopefully not carrying my laptop and walking around, but small device. I'm now walking at pedestrian speed, 3 kilometers per hour. I now model this as a Rayleigh situation, Rayleigh fading situation, and I get this curve. So fixed environment is not as both have multi-user diversity gain, but the fixed is worse than the low mobility. Okay? So mobility is better. And here's why. And here's why. And basically, in this business of opportunistic communication, you basically want the channel to fluctuate as much as possible. Because all you care about is not what the average channel behaves, but how the peaks are. The more peaks there are, the stronger the peaks are, the better you can gain from this opportunistic method. And we can see it here. In a mobile environment, the channel is fluctuating like crazy. And they're fluctuating very fast. Fast compared to what? Compared to your latency time scale, which in this simulation is 1.6 seconds, so 1,000 time slots. Okay? So I have like a total latency of 1.6 seconds. And you see a lot of fluctuation. Peaks are high. In a fixed environment, with respect to the same 1.6 seconds, the dynamic range is smaller because only a part of the environment is moving. And the fluctuation is slower because, I'm not really moving. Okay? So therefore, peaks are higher and they come more frequently in this situation. And therefore, you get a better gain. Now, I have a third curve here. And in this third curve, I have high mobility. So you think, low mobility, gain over fixed environment. High mobility should gain over low mobility, the right direction. But no. In high mobility case, you don't have multi-user diversity gain at all. Can anyone tell me why? So this really points out a system requirement for implementing this opportunistic strategy. The basic thing that opportunistic strategy needs is what? Is channel sign information at the transmitter. Not at the receiver, but at the transmitter. To get that requires feedback. Feedback has delay. You measure something, you process it, you do round-trip communication. There's a certain delay associated with that. If that delay is long compared to how fast the channel varies, then you can't track the channel. You can only shoot for the average of the channel. So you're essentially back into the fast fading without CSI situation. And if I lost that, then I have no multi-user diversity gain. And that's what happens in high mobility. So when you go to vehicular speed, this technique is not very useful, at least in the current EVDO system. Okay, so that's the limitation of the technique. Okay, so one can think about how to close the gap here. So the next thing, so now I've talked about in this historical development of these ideas. I've now talked about Goldsmith and Varaya, Knopp and Amblay, proportional fair scheduling, and now the fourth idea is coming. The fourth idea is based on the observation that there's a gap between red and blue. Okay? There's a gap between red and blue. How do I close that gap? Is there a way to close that gap? Now, why is there a gap? There's a gap because there's less randomness in this channel. Okay? So I gave this talk at some prestige university, whose name I now don't mention anymore. And I gave this talk, and I showed these pictures, and a prestige professor asked me the question in the audience. He said, you know what? I think we should do something about this. If you have no mobility, if you have a fixed environment, then maybe we should, move the base station around. Carry the base station on top on your shoulder, move it around, do something to it. Even better, get the grad students to move them around. So I think that's the one problem with academia, like exactly what Alon did earlier. When you're stuck, when you can't do anything, you say, get a student to do something, And that's not good. So these ideas are not the greatest idea. It's not very practical, but turns out that there There's a way to do it electronically. So the next idea I want to tell you is that in an environment where there's not enough fluctuation, you can actually induce fluctuation. So now we sort of turn the problem around, right? Because before, we were worried about these fluctuations, and we want to provide diversity to remove them. But now that we saw that fluctuation is actually a good thing in optimistic strategy, if there's not enough, then we should try to induce them. And that's the next idea. And that's the idea of dumb antennas. Dumb antennas. Okay? By the way, dumb refers to the antennas and not the authors. Okay? That's right. That's very important to clarify that. It's very important to clarify that. And here's what we do. Before, we were talking about basically one transmit antenna. Now we use two transmit antenna. So we have already seen two transmit antenna before when we talk about Alamuti, etc. But we're going to use it in a completely different way here. So what I'm going to do is the following. I send the signal that I was going to send through my one antenna. Instead, I send it over two antennas, where xt I send directly through the first antenna. And then I do a phase rotation. I do a phase rotation, okay, on the second. And this phase rotation is, I'm going to vary it with time, okay? So it's multiplied by a time-varying phase here. The signal will go through two channels, H1K from the first transmit antenna, H2K from the second transmit antenna, to each user, K. Okay, that's what I'm going to do. So if I do that and I vary the theta of t, let's see what happens. Okay, so suppose I have a fixed environment. So both the red and blue user, they're not really varying a whole lot here. It's low dynamic range. Okay, if I do this strategy, it turns out that it looks like this. This is a cartoon, of course, but roughly speaking, it looks like this. So the red and blue are going up and down like crazy, and now I can apply the optimistic strategy to this. And moreover, the more important thing is the red and blue peaks are not synchronized using the strategy, right? If you use a single transmit antenna and you move your power up and down, then of course you get peaks and valleys as well, but then they're synchronized and it's kind of useless because when they go down, both guys go down. So then the key here is that I was able to induce the fluctuation such that the fluctuations are still more or less asynchronous in terms of the peaks. Okay? So let's see how this works. So to do that, I have to give a sneak preview to my last section, which is on MIMO. And I'll use the word beamforming here in a bit of a loose way. I'll make it more precise in the last section. Okay? So idea is the following. If you have one transmit antenna, you send signal in an omnidirectional way. And that is, no matter where you are in free space, your received energy is the same. When I have multiple antennas, what one can do is to do beamforming. Okay? In fact, we already talked a bit about that yesterday, but now I'm going to draw some pictures. So what is beamforming really? Beamforming is essentially saying that the signal I send in one antenna and the signal I send in another antenna is delay with respect to each other. So that the delay controls essentially the direction at which the signal goes. Okay? If you think about it, if I change the direction, if I change the phase of the signal, then at a certain direction, which is a function of the difference, the signal will constructively add. At another direction, it will constructively destroy. So in other words, I am basically using this phase to control my beam. Think of a flash lighthouse. By changing theta of t, I'm changing this beam. Okay? So that's what I do. I'll go through a bit more math later on, but that's the rough idea. So what do dumb antennas do in this setting? Dumb antenna sweeps the beam and change the theta of t, so it sweeps the beam over all directions. So let's draw some picture here. So let's start with the base case. Suppose we only have one user in the system, okay? And we do this dumb antenna phase rotation. So let's see what happens. So now the beam rotates. So this is my beam. As I change theta t, this beam rotates. Now you notice that there's something wrong here. Most of the time, the beam is pointing to nowhere. So therefore, this is a bad idea. You don't want to do this for one user. Because most of the time, you send the beam to some random direction. Okay? So this is no good. Most of the time, beam is nowhere near the user. Now, in the case of multiple users, which is our setting, the story is different. Why? Because as I rotate the beam, now my population is very dense. So wherever I point, there will likely be a user which is close to that beam. And what is that user going to do? That user is going to report its SINR, which essentially says that, you know what? Hey, the beam is close to me now. Schedule the traffic to me. Okay? And that's essentially what happens. Now, you can imagine a scheme whereby one can actually explicitly point the beam to a particular user. We talked about that yesterday. We talked about transmit beamforming, right? What is transmit beamforming really in this picture? Transmit beamforming is essentially saying I measure the channel gains from each of my antenna, and I feed back the information. I align my phases such that the signal constructively add to the receiver. What that does is essentially saying I figure out where exactly all the users in my system is through some measurement and feedback and a lot of work. And then I figure out, so if I point this direction, I'll hit this user, point that direction, hit this user, so I can schedule now and do the transmit beamforming. That requires a lot of feedback, a lot of measurements. Okay? What this idea says is that, no, you don't need all that. In fact, you don't even need the receiver to know that you have 2 or 3 or 5 transmit antenna. All he needs to do is to measure the channel and tell you, is your beam close to me, basically. Okay? And he reports the information. And then you can get essentially a performance that is very close to the transmit beamforming performance. And the reason is because if you have lots of users, there will always be a guy very close to the beam. And that's the idea. So by transmitting that user close to true beamforming performance achieved without explicit knowledge at the base station of the knowledge of the locations of users. So we apply that idea, and this idea is done with Pramod Viswanath and Rajiv Laroya at Flareon, then Flareon, now Qualcomm. Everything is sort of converging. The performance gap between fixed and mobile was reduced. Okay, so if I apply this technique, I can remove this gap. So you can think broader about this concept, and you can compare it to smart antennas. So now, the smart people meets the dumb people. Let's see who wins. All right. So smart people are what? Alamoudi is a smart person, right? He invented space-time codes, Alamoudi schemes. So we can ask the question, should we implement space-time codes in EVDO, or should we implement dumb antennas in EVDO? Now, space-time codes, what do space-time codes do? Space-time codes increases diversity, okay? So if you're in a slow fading situation where you have to get the traffic through very quickly, you can't wait for a better channel, then space-time code is definitely useful, reliability. However, in a setting that we've been considering where we have latency timescale, which is significantly longer than the variation of channel, then space-time code is actually reducing the multi-user diversity gain. Why? Because space-time code is essentially working the opposite direction. It is reducing the amount of fluctuation. Okay? And so less multi-user diversity gain to achieve. Dumb antennas are not the greatest idea if you deal with a slow fading situation, not necessarily good. However, it will add fluctuation, and in a fast fading situation will increase the multi-user diversity gain. Okay. So let's finish this. Yes? Yes, yes. That's right. So yes, exactly. But in the context of, that's why I mentioned, in the context of EVDO, right, which does have this partial CSI. Yeah, good point. Okay. So one more thing. What is the effect of doing this on a cellular level? So if you think about a cellular system, then we have multiple cells, okay? And then we can talk about doing this dumb antenna, okay? For each cell, what is the effect of the dumb antenna on the system? So if you think about multi-user diversity in EVDO, the user whose channel is good essentially effectively means the channel has a very good signal to interference noise ratio, right? Remember, in the cellular system, we always think about signal to interference plus noise ratio because the interference from the other cell may be important. So what we're doing here, when we do scheduling, multi-user diversity scheduling, is we're scheduling to a user whose not only the signal is strong, but also the interference from the adjacent cell is weak. Okay? What dumb antenna do now is not only you're pointing the beam within the cell of interest to that user to get a strong channel, but you are also rotating the beam for the interfering base station so that there will be times in which that beam is pointed away from this user and therefore create less interference and therefore an opportunity to schedule that user there. So this is opportunistic nulling. So beamforming not only have an advantage of pointing the beam to the user of interest, but also pointing the beam away from a user so that the interferer won't kill it. Okay? So, so dumb antennas provides opportunistic nulling. We talk about interference averaging. Okay? In a CDMA system, interference averaging was a good thing because it makes the interference more consistent. In an EVDO system where you do multi-user diversity scheduling, interference averaging is actually not so good thing. Why? Because I don't care about the average. I care about the peaks, and the peaks arise when there's no interference. So I want to make sure that the interference fluctuates wildly so that there will be times in which there's no interference so I can schedule that user. So therefore, interference averaging is a bad thing. And if this guy is in the range of several base stations, or maybe several sectors of then interference averaging reduces this performance gain. Okay? So the moral of the story is, if we conclude this, it's too much stuff here, forget it. The moral story is that if we want to think about the use of a technique, then we really should think in the picture of the whole system. And this, I think, is a good story in the sense that it tells you how you can go from a theoretical idea slowly, step by step, into a practical idea. And that practical idea is obtained by considering not only the theory, but also how the whole system behaves, and to make sure that the theory works in sync with the whole system. Okay, so let's rest for 10 minutes, and then we'll talk about MIMO for the last section. Okay.